Now, this is what we call combined loading, okay? Combined, so up to this point, we just, for the most part, had just one load being applied. And in this case, it's true, it's one load. Now, the difference is that prior to this lecture, everything was in the center, right? It was perfectly at the center, right? And in real life, you're theoretically never going to get loads exactly at the center. It's going to have some kind of slight offset, right? So in this case right here, you know, you've got the member. If the load was right here, whatever that P load is, the stress, would equal to P over A, right? And we would be done. And we'd just be like, okay, well, that's it, guys. We're done with axial stress, and that's about it. Now, because it's offset, right? Because it's offset, what it does is it actually creates this moment, right? And what is that moment? Moment is equal to force times distance, right? And the force is 15 kilonewtons, and the distance is going to be 50 millimeters. Right? So it creates that moment, right? Hopefully you can see that. You know, one way of looking at it is that, you know, let's just say that this is kind of you. Let's say you're able to go to Costco, right? And you had your hand out. Now, if you had like milk and you put it right on your head, it would go straight down and to your legs, and that's how the force would flow. But if you're carrying your milk, like say a gallon of milk or something like that, right? It's right here. I don't know if you noticed, but if you just have 1 gallon of milk, you're going to feel your body wanting to rotate this way. And so what your body has to do in return is, in your core muscles, you have to push it up that way. Okay? Does everybody get this concept, and does this make sense? Now, what happens is that if you get the milk here and put it on the other side, get another 1 gallon of milk, all of a sudden, this does not appear because it cancels out each other, right? So this wants to do this, and this wants to do that. They cancel each other out. Therefore, your abs are no longer in a workout position, right? And so the moment that I said moment, the moment that we take this out, what's going to happen is that load is going to come back in. It's going to rotate, right? Does anybody have a question about this concept? So we're going to move fast. If not, no question. Okay. I guess that's an old one. Okay. So what does that mean now? All right. In the morning, I like to watch TV. Right. Now we also have to do a thin wall structure, so I'm going to put TW for thin walls. Okay. So do we have an axial load? Yes. Do we have a moment? Yes. Question is, do we have a torsion? No. Do we have a shear? Because we have moment, theoretically, you don't have direct shear. So I'm going to say no, because we don't have direct shear. Yeah, so yeah, there's no direct shear. We would have the shear if it was in this direction. Okay. And then there's no thin walls, so then we have, so wait, torsion, we said no. So if this is the case, this is how I go, and I go A is equal to stress is equal to P over A. And then moment is equal to M, stress due to moment. Well, yeah, moment is stress is equal to MC over I. So you notice how now moving forward, everything's going to build off of what we learned. So we're not going to have any new formulas, okay? So we'll make sure everybody understands that. So we have this kind of combined loading, right? And so we look at the loads. So we have P over A, so stress is equal to P, which is equal to 15 kilonewtons, and area is going to be 40 times 100, right? 40 times 100, right? And then M, stress due to moment, right? And I'm going to do plus or minus, and you'll see why. I'm going to put plus or minus stress due to, let's see, moment for fun. It's going to be the moment, which is going to be moment is equal to 15 force times distance, which is 50 millimeters. I'm just going to keep everything in consistent millimeters. So I don't know what that is, 25 to 5750. Oh. Okay, so we have MC over I. Now, this is a great picture because this is where people will get really confused. They're going to be like, okay, wait, is my moment inertia, like, is it this surface? Wait, is it this one? Or wait, is it this one? Right, remember when I said in strength of materials, for the most part, we're always talking about cross section, right? So what that means is that I have this member and I'm literally taking a knife and I'm cutting this face and I'm looking at it. So what I'm trying to say is that is the surface where I am looking for the moment of inertia. So what does that mean? If I was to project it, right, and kind of draw it out, this is 100 millimeter, and this is 40. On the final, you were expected to be able to look at something that's 3D like this. Also identify that this is what you're looking at in moment, and know that you're bending along that axis, and that is the goal, right? You know P over A, you know MC over I. You kind of knew this surface, you kind of knew this, but for the final, you've got to own it. That's what it comes down to. So what does that mean? We know that for a rectangle, I is equal to 112 base times height cubed, so it's equal to 112. The base is equal to 40, and the height is equal to 100 to the third power. I don't know what that comes out to be, but what I'm trying to say is that, and then C is, remember, here is what we call the neutral axis, and C is going to be from the neutral axis to the extreme end. So in that case, it's going to be 50 millimeters. So therefore, what this means is that we have the M, 50 milliliters, and 750, sorry. I is going to be whatever this is. And so all of a sudden we have the stress due to axial, and then I put plus or minus, right? And you'll see what I mean by that. 15 kilonewtons, yep, we got that. 112 base 40, we got that. 7, oh, I was off by, oh, kilonewtons because of the zeros, yeah. Maybe my O's are off. Put some of that. Okay, so MC over I, we got that, right? So we have that this and this, and I'm going to put a plus or minus for them, and you'll see why. This is stress due to P over A, pure axial, meaning that a load is being applied and you have a reaction, constant reaction throughout. Okay, now plus it's saying the bending moment, right? So which is weird because you're like, okay, it's 11, and so what they're trying to do is right here it's up and this is down. Okay, imagine this. I was just watching the show Outer Banks, and so I think it's giving me motivation to draw this. So I just finished the season 1. It's #1 on Netflix after, what is it? Tiger King. So yeah, I watched Tiger King too. That's what we're doing now. Okay. So imagine you're on a boat, right? Can you imagine that if y'all decided to party and do this, you'll notice that the ship would start to kind of do that. You guys follow? Yes? Yes? If you've never been on a boat before, I don't know what to tell you. Chat is quiet. I need some kind of confirmation. I have students right now. Yes. Okay. Okay. So everybody understands that this whole boat can kind of go there. So then can you see that if I was to draw these stresses, that it is like this and like that? You guys follow? Let me do a different color. Down. We agree? Yeah. And so if I was to kind of draw a line from here, and I would draw this like this, you see how the moment diagram also is being developed by this Outer Banks, right? Because this is creating that moment, and because of that, you'll see the ship rotate, which in turn creates that moment diagram. Not moment diagram, moment stress. In other words, it is not constant. It is, it's down here and up there, right? You see that? So you see right here, they're trying to do the same thing. I just don't like how they're drawing it. They're doing, down this way and up that way. But the idea is the same thing. Up, down, right? Equal and opposite. What that means is that here, everything is pushing up. If you take here, you'll put it on this side and push it down. You'll take this one, which is pushing it up right here. So if we have 11.25 up, and this is also up, we're going to add these two. Right here, this is down. When we say up is positive, this is negative. What that means is that if we take 13.75 plus 11.25, then we're going to get 1415 MPa, right? And if we take 11, we say we take 11 point, sorry, it was 3 up, so 11.25 down and 3.75 up. We're saying up is positive. You're gonna have negative, I don't like doing this math, 0.5, 6 or 7? Yeah, 7.5. And that's how you would do the stress at individual portion of the block, right? So the way to think of it also is that I'm putting a sensor right here and I'm putting a sensor right there. What does it feel, right? Or rather right here. That makes more sense, right? So if I was to kind of apply the load right here by standing on it, this is going to rotate down this way due to the moment, right? And then we've got a force that's coming down. Can everybody see this? Like, not just see the screen, that is, or understand visually what I am trying to convey is really the question. And I'll screen over, see if anybody has questions. I just have a bunch of yes. No questions? Okay. All right, that's an easy question. All right, so this is interesting. So here, what we have tank has an inner radius of 600 millimeter, thickness of 12, filled at the top of water, having specific gravity of 10. It's made of steel, having specific weight of that. Okay. Determine state of stress at point A. Tank is open at the top. Okay. So specific weight is just giving you the axial load. Okay. Oh, it's kind of a pain. All right. So things gamma, right? So this is just really translating to getting weight. Because if you have density, which is, I guess, referred to as that way, times volume, right, you'll get the weight. You all agree? Yes, assume yes, right? So by doing that, we can find out what the weight of the container is, which is steel, right? And then we can do the weight of the water. And so, you know, if it's 600, V is equal to 2 meters is 0.6 meters over 2 squared pi times the height is 2 meters. That's what it would be. Times the density of water, gamma, which is equal to 10. So you multiply these two values, or this whole entire value, you'll get the weight of the water. Right? For the steel, it's just going to be that we have to calculate. So we have to calculate inside outer radius, right? So it's going to be pi d. Let's just make it simple. R outer minus R inner squared times the height, which is equal to 2 meters. The outer is the inner is going to be 0.3, and the outer is going to be 600 times 2 of that, right? So d outer is equal to 600 plus 24 millimeters, which is equal to 624 millimeters, and divided by 2 gives you radius, and that's going to go in there. Okay, when you do that, oh, they did. Why is that? Should be, oh, they're probably doing something right there to pull it out. So it's essentially going to give you the same value. No, 78 is going to be the density. So, so again, it's volume times the gamma value is equal to weight. So we have the weight of the steel tank. Pressure of the water tank at level A is, okay, so that's pressure. Hold on. Did they not do the water? Did they not calculate the weight of the water somewhere? I don't know. They somehow did it. I don't know where they did it, but they're supposed to do it somewhere. Anyways, the pressure is just, I don't know if you guys taken fluids, it's just really going to be your density multiplied by your height. And in this case, it's 1. Oh, that's what it is. So, oh, duh, that's what it is, guys. Okay, so I'm going to take back the height. I initially said that the height was 2 meters. But what the question's asking is the stress at point A. So in that sense, they want to know what it is at this point, not at that point. And I took 2H because I thought it was at the, I thought they wanted it there, which is not the case. So that's the difference. Okay, so now that makes sense. Okay. Now, because you have all that stress, you got, what you're going to be taking a look at is, let's see. So it is, there really isn't an axial load in the wall besides its own weight. But in this question, it's saying that there's none, but there kind of is, because you can actually assume that the self-weight is actually right here all around. But they've ignored it for this one. Is there a moment? No, because it's right at the center. Is it torsion? No. Is there a shear? No. The thin wall? Yes. So really what we're doing is that we're going to find out what the stresses are. So here, what we'll find out is, oh no, I'm sorry, I'm going to take it back. They did consider axial load. Great, good, good. So really what we have is we have the longitudinal stress, which is just part D, right? So the pressure is 10. So the R is the radius, right, which is the 600. Oh, that's what it was. They've already given me radius, so it's not diameter. That's where it was off. Okay. Anyways, so you've got the pressure, you've got the radius, and you've got the thickness, because they give you the thickness right there. Okay. And so what you'll have is that you have a longitudinal stress of 500 kilopascal, right? And then you have an axial load, right? And so the axial load is in compression. So let me just kind of do it this way. And this wants to expand outwards, right? And so it's the total weight of the steel divided by the area of the steel. So that is correct. The question that somebody may have is like, well, what about the weight of the water? Well, the weight of the water, while it is applying a load here, the water pushes it outwards, right? So really the weight of the steel is what I drew here. And so the book is doing it correctly. That's the weight of the steel, right? So what they're doing is that they're finding the longitudinal stress, right? And then also we have a gravity stress, right? So it's just going to be P divided by A, right? Force divided by area. That's all it is. Hopefully you guys are catching on to very familiar formulas and how we're considering it. So essentially what you see is that we've got 500 in the principal flowing out, and then in the other direction we have 77 kilopascals that's applied. And so yes, so that's that question. Now I'm trying to think, let's see about this problem. Let me see if anybody has questions. So this is a really good question. Adriana has asked, do we have to draw the stress diagram? So on the final, you're going to see something that you'll solve a certain way, and then you'll draw that stress diagram, and then you'll do the Mohr circle, right? You see how this thing is building up. Again, there's, for the most part, nothing new. It's just that we're building onto each other, right? So right here is, the arrows went to the direction and all the way around. That's a good question. So the question is, how do we know that the arrows went one direction and not the other way around? Okay. So that is a So what's being asked is, why is this one this way, right? And why is this, is that right? Sorry. Why is it 500 that way? Okay, so that's a good question. So let's look at what the PRT definition was. And the PRT means that it is tangential. And so, which is the hoop direction, which is in that direction, okay? So that is the hoop direction. And it's always going outwards, right, in the hoop. So if I was to cut it this way, it would go this way and that way, right? So if I was to draw it, it goes out like that, 500. And the axial load is compressing it due to the sigma there. And that's how what you're getting. Okay. So what it's saying is that if we were to take a little strip right here, a piece of it's really saying A, right? Because it's, but I'm just moving it up so you can see it. Now the weight, gravity is compressing that material. And we know it's hoop, it's pushing it out. So that's your 500 and that's your 70 something, 77. That's your stress block. Does that answer the question? I'm glad I can answer questions. Great, good stuff. All right, so this is really cool. It's not really cool, it's kind of a pain. But you know, it's, again, I want to remind everybody, shear moment diagrams. I will promise you that there will be a shear moment diagram on the final. On the midterm, you were only asked to draw a moment diagram. On the final, you will be asked to draw a shear moment diagram. And so keep in mind, if you're still struggling, I would dedicate this week for you to sharpen that up and make sure you don't fall behind on the shear moment diagram, because on the final, if you're right at the cusp of passing or failing, what I do is I look at your shear moment diagram, and if you totally did fine on the shear moment diagram, what I will do is pretty much you'll pass class, essentially. And I really don't want to fail anybody, so. Anyways, so here what it's saying is that determine the stress produced at C. Okay. State stress loading in the procedure at point C. So pretty much what you'll do is you will solve for the reaction, right? And then what you could do is you could take an internal force and cut it. So I'm not going to take the reactions. I'm going to assume that you could solve for reaction. That's, again, a static review. You could just figure it out and do it yourself. So the question is really at point C, right? If we were to cut it, what would it mean, right? So let's see. If I was to cut it, you have an unknown out here. These are all unknowns, okay? So we cut it, the question is, what is it, right? So we know that if we look at this, it's 16.45. It's an equal and opposite, so equilibrium says I have to do 16.45 this way. So that's good. Here it's telling me it's up, so that's got to be down, and it's got to be 21.93. So that's good. The other thing is, if I take a moment about here, I have a force times distance, okay? This does not, it's concentric. Here, you have a lever arm of, I think it's 2 meters. Here, because I think that's how they did it. So you have a force times distance. So moment is equal to force times distance. Your force is going to be 21.93. Your distance is going to be 2. So that's 6, 8, 2, 2, 4, wait, 2.86 would be your moment. And so it is acting in this direction. So you want to go in that direction. So 42.86. Okay. My bad. C is at 1.5. I don't know what it is. If somebody can, well, the number is posted anyways. Okay, so what does that mean? Okay, so let's go to our checklist. A, M, T, V, thin wall, right? Thin wall, no. Axial, yes, we do. Moment, yes, we do. And it's 1.5. Torsion, no, we don't. Shear, shear. Yes, we do. So what does that mean? Stress is equal to P over A. Moment is equal to MC over I. Shear is equal to VQ over IT. Ta-da! That's all you do. So P over A, yep. MC over I, yep. And did they not? Oh shit! They didn't do VQ over IT. Why? Shit! Why didn't they do it? Oh, that's why. So there is a shear stress, but if we have a rectangular section and we were to draw this, and this is like a midterm review. Remember, for rectangle, the maximum is at the center, and that's 2/3 or 3/2 V over A, right? So if it's rectangle, you could just use that equation to solve it. Now, what's happening is that at the tip, we know that that's 0, right? And C is at the very top. And so if we were to take this and draw it, C is at this point, which is then 0 for shear. That's why, while theoretically there is shear, your Q, which is equal to Y over A, your area is 0, because you would take the area of just that point, which is theoretically 0. Therefore, your VQ or VT is equal to 0. And so that's why it's not considered in this. Now, if, for example, I was asking for what would it be there, then you could do that shear stress is equal to VQ over IT. If you knew that that was a rectangular shape, then you could just say that V is equal to 3 over 2. You could say that 3 over 2 V over A. This, for rectangular, is essentially at the center, at max, is the same formula. It's derived. If you're bored, you could derive it. It'll come out. I've done it. Okay, so we agree that we've got that, and we've got that, right? So remember that the shear stress, let's see, it's this way, so it's downward, so it's compressing it. And so you have it going inwards, which is compressing it, right? Shear, it's 0. And then now we have the bending. Now the question is, which way is it bending? So the bending is bending this way, right? It's bending that way, right? So this is 1.32, let's just say to the left side, right? And this is 63.29 to the left. and this is 63.16 to the right. What you'll do is you'll left plus left is add. So you'll add these two. And right here, you'll add and subtract. I don't know what the hell the difference between this and this is, but it looks almost exactly the same. Okay. And so at the C portion of it, we have that, oh, because the C is at this tip right here, that's all we care about. So we're at 1.32 plus 63. So it's going to be like 64.48 or something like that. 64.5. Yeah, so you'll add it together. That's what we said for the top portion, add and add. Any questions? Oh, thanks for. Okay, great. David, so we're gonna go. Alrighty, so this is it. So once we go over this one, we're pretty set, and so you're pretty much ready for the final after we go over this problem. How much time do we have? Let's see. When I do this, they don't tell me what is this? 18. Oh, yeah, we can. Okay, now I'm not gonna put in all the numbers. We're gonna just talk about concept. If you can see this, you're good to go. Imagine that this is a boat. Right? And let's just say that the center of the boat is here and here. Do we agree? You're gonna say, yeah, I agree. Right? And I'm right at the center. That means I have equal pressure everywhere. It's constant. Well, ignore water pressure being like kind of a, or we should just assume that it's flat or something like that. Okay, so we would have a constant pressure being out. Now, in the first example, we talked about moving this way along that line. And what does that do? That tips the boat along that axis downwards, right? Right, along this axis. So if we were to draw this axis right now, it tips it like this, right? And that's essentially drawing your bending stress diagram, right? Here's your neutral axis, which is the center of the boat. Now, if I bought a rectangular boat and then I walked this way, you could see that about this axis now, I'm going to draw this axis, which is this one, it's going to tip that way. So one axis, it's tilting this way, the other axis is also tilting this way. So that means that at point C, this point, you'll have the most stress, right? Because it tilts one way and the other way. Any question on this concept, anybody? So in summary, the very first question, one axis to give confirmation and all that stuff. Be above this way on that axis. You see that? Now, if I was to take that load,
Wait, Professor, can you repeat that entire last like 5 seconds of what you said? You went in and out.
oh, okay, great. So are we talking about this one, right? This example starting over? Yes. Hopefully this is.
The last part before you went out was you just finished drawing the green diagram on the left, on the right.
This one?
Yeah, you just finished drawing that.
Okay, okay. So, okay. So right here, what we were saying is that as you walk from here to there, right, you're gonna not only rotate it about tilting it this one way, but you're also gonna be tilting it the other way. And so another example would be if we had a flat, say, book for fun. Okay, this is assuming that everything can stay in equilibrium. Let's just say that you use your finger, oops, and you're holding it right at the center. Here's the center, okay? So if I and draw the axis. You guys see the two axes, right? So if I apply the load right along this axis, right at the center, you'll see that the book will want to, about this axis, it's gonna rotate like this. You guys see that? Based on this load. So it bends about that one axis. Now, if we take it and move that load over to here, not only will we have our first rotation, right, but we'll also rotate it about this axis, this way. So what that looks like is that it's really hard to draw, but what ends up happening is that this corner goes down and that goes up. And it tilts that way. If you can't see this, just get a book, put your finger at the center and try to like balance it and just push on the corner. What you'll see, it's going to rotate one way and the other way. So it's a double axis rotation. Does everybody see this or understand it? I'm not an artist, so yes. It seems like David is yes. He's Mr. Yes. Okay. So if we do that, what we have is we have bending about one axis. So let's just say that that is the y-axis. So we have m on the y-axis and m on the x-axis. What that means is that we're going to have mc over I in the x and mc over I in the y. Stress x, stress y. So you have pretty much bending on one axis, bending on the other axis, and because of that, you have an axial load. So in summary, what that means, so we go to our checklist. A, M, T, V, thin wall. Okay. No thin wall, right? Do we have shear? No. Do we have torsion? No. Do we have axial? Yes. Do we have moment? Yes, but we have stress, stress X, stress Y. That's what we just did. And that's equal to MC over I, and that's equal to MC over I. And that's a different MC. These are X, X, Y, 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 X. That's the difference. That is the summary, and from there it's just plug and chug. Stress, P over A, max, M, X, C, X, I, X, right? Here, M, C, Y. This should be a Y. This is incorrect. I typed it wrong. 375. Okay. And so you add it, right? We have the constant axial load called normal, bending about this axis, bending about this axis. Okay. And what's the question asked where it is? Largest. Right. So largest means that we take every corner and find out. Remember, extreme away from the neutral axis is going to be your maximum, right? So that dictates the ABCB point. So let's think about it. So before we even look at the number, let's just visually locate where that would be. Okay. I don't know if you guys seen it. There's this thing called It's Not My Kids. It's a movie, and so that's what we're going to do. We're going to go in. Okay, so first what we'll do is we're gonna go to center, choose a side. Okay, if my load is here, is this gonna feel more compression or is this gonna feel more compression? I'm gonna say this one, right, great. So now we know that between this location that this is gonna be more, right, great. And now we're gonna do it about this axis. And the question is, where are you gonna feel more compression, either at D or C? So where are you going to feel more compression, D or C? I mean, if you look up, that load is directly above you. So we know that C is going to give us the maximum stress. What that means is that we will take stress plus stress in the X plus stress in the Y. We'll give them our maximum stress axial load. X axial. So you're going to add all three stresses. The combination of other locations is going to be stress axial minus plus sigma x minus sigma y. Another one's going to be y minus sigma x minus sigma y. So you see that there are like these different combination which resorts to if you're standing over here, if you're standing over there. But really, we want to find maximum, so it's at C. So without calculations, we can visually see it's C, and ta-da, C. There we go. Easy, easy.
Professor,
Question. Yes.
will you be uploading the video as well in case when we study, we could go back to it?
This is something that you guys would enjoy and love for it to be uploaded, huh?
I just like to go back. I really like the way you, like that I could go back and then just like pause it and then kind of work it out and then continue.
This lecture will be uploaded.
Thank you.
Okay. Any questions? Let's go back to the questions. We're good? Waiting. No questions? Yes. Dixie had a question. Or did you ask your question? This was delayed. No questions. I think your question was, will this be uploaded? So the answer is yes, this will be uploaded. And it will appear under lecture, and then it will be titled something Zoom lecture or something like that. And remind me to do it tonight. If you don't see it up by 10:30 p.m., just please send me an email. That's when I'll be pretty much done with class tonight. So, all right, if that's no question, then I will see you guys next time. Okay. Yes, Brian. Yes, Brian. Can you ask your question? Do we have to draw the figures at the end? No, you are not required to draw all those three figures. That's just a visual feedback to tell you what it is. So you can see how everything is. So again, it's just feedback for yourself. But in your mind, you want to visualize it because that's going to be the best way to understand what the answer is, okay? So while you don't need to, you're not required to, if you can draw it mentally, you can visualize where the answer is. And again, going back to this, remember, we knew that the maximum stress was at C, even though we didn't do any kind of calculations, right? So you want to be able to visually do that. The homework will be challenging. This whole thing will be challenging. Now, what I want everybody to understand is that with the new introduction of thin walls, with the exception of that, all the formulas are the same. So all this chapter is asking you is, did you or do you understand, or did you understand? And really your answer is, yes, I will, because I need to for the final. Hopefully that answers your question. Okay. It's a fun chapter. I know it's kind of hard, but as you start to see it visually, start to connect things, things are going to come together. That's why I love this chapter. Yes, exactly. It puts all the stuff together. And so this is not an FE exam requirement, right? On the FE exam, they're not going to ask you this multi-loading stuff. I really doubt that they're going to do it. But what this does is that you can see how all the chapters come together, and you can start putting things that you see around you in real life all together and start, doing the AMTV checklist and all that stuff. So hopefully that makes sense. Again, the lecture will be uploaded. If there's no other question, I'll see you next time. 3, 2, 1. Okay, and I think people are signing off. All right. Thanks, everybody. Oh, is there a question? No? Everybody's leaving. Okay. All right. Bye, guys. Why can't I exit? Oh, gosh. I'm trying to hit exit. It doesn't exit.